We are going
Go ahead.
to step from the glorious present into the glorious past. And we are going to take a look at an older system that Czech should be familiar with. And it is going to be this little puppy. This nice little rectangle that you're looking at here is a NOVIX 4016. The whole thing is an EB1 experimenter's board, which was sold in the mid-80s, like 85, 6, 7. I forgot, I slept since then. From Forth2020 Flash in Germany. Board layout is fairly simple. This is almost original. With two replacements. We have the CPU. We have a little gate array logic for memory decoding and a couple other things. A TTL to plus minus 12 volts for the serial port. Serial port is here in the upper left corner. We have 2K by 8-bit static memory chips for both the data and the return stack. We have 32 kilowords of main memory. And we have the firmware into EEPROMs, and these two EEPROMs are the only update to this board since I bought it from Ulrich way back when. The original board on these two positions had EEPROMs, the one with the quartz window. And after I powered this board up after all these years, it had survived in my mom's nice, dry, almost temperature-controlled attic for 30 plus years. Powered on the board, it came up, it worked. Powered it off right away, packaged it up, brought it back to the US. First order of business, EEPROMs are not supposed to hold contents for 20 plus years, much less 30. Get them offloaded, get the contents burned into something else. And there's our first problem. Do I trust some programmer from China with questionable documentation with chips that are irreplaceable? This is one of the known two existing boards. Ulrich has the other one. Yeah, let's be a little bit careful with that. So I spent easily a year designing my own EEPROM reader writer. Learned a lot that way, like how to program Arduinos to drive that. Relearned how to read chip timing diagrams. Those are fortunately easy. And I learned KiCad to make my own boards, because this breadboarding with too many wires gets old very, very quickly. So long story short, I tried FRAMs first to find out that FRAMs need chip select, set and reset for each access. This board doesn't do that. Oops. So FRAMs would have been very convenient. They're out. Now we are talking EEPROMs. So this is the only change to the board. You have a Eurocard connector here on the right. The only connections are power and ground. Takes 5 volts. And on the other hand, on the other side, a regular serial port. The CPU is interesting inasmuch, I'll drop the link into the chat when I'm done. There is no microcode on this thing. There is an ALU. There's two input registers, T and Y, has stack pointers for data stack and return. If we take a look at the instruction set, it's deceptively simple. This CPU does not have any microcode. It has 4,000 gates in it. Think AND, OR, XOR, maybe a NOT here and there, and that's it. 4,000 gates, a low transistor count. There's no microcode, so all instructions talk directly to parts of the CPU. That makes taking them apart mentally kind of easy. If the highest bit is a 0, all instructions are 16 bits. If the highest bit is 0, the rest is an address. It's a subroutine jump. Since the address of the subroutine is 15 bits, you can logically jump to a location within the lower 32 kilobytes. If the upper 2 bits are 1, 0, then it's a conditional, and the address shrinks to 12 bits. So if you want to get out of your 12th bit addressable segment, you have to jump through a subroutine and do your branching somewhere in there. So if the upper 2 bits are 1, 0, the next 2 bits specify which conditional it is, and here's your target where you go. Okay, ALU operations. 4 upper bits are 1,000, 1,000. Then the ALU function select, and a little bit of input control and some other goodies. Nice to see here your return, from subroutine get its own bit, which means you can do an operation in one instruction and return from subroutine at the same time. What else do we have? Memory references. Well, it goes on like this, but it also ends fairly quickly because you have read-write control, user space register transfers, load literals, and that's it. The rest of this document is command summary. Again, deceptively simple, but it is up to the firmware to decide what to encode where. Makes for a nice small board. Power consumption, I have no idea. I replaced the 220 volt power supply with that I wired myself with a store-bought 5 volt 110 because I didn't feel like doing this mess again. So let's take a look at the board. What's on it? Nothing happening. Why is there nothing happening? Oh, right. I need to power it on. This thing is not directly hooked up to my laptop since I want to mess with it when I feel like it and I might not be at home. This is internet reachable for me. The way how you control this thing is it's hanging off a remote operatable power strip. So it has a serial port in and it has a couple of outlets, in this case too. Let's turn on the board on 2. Clickety, am I sure I want to do this? Yes, sure. Okay, the board has power. We change the screen, go over here. Nothing happens. That was stupid. Power this thing off. Yes, dear. Power it back on. Say yes. So the board is on. We hop back over here and we hit the letter B. It uses the letter B to calculate what bit rate this is running on. Remember, you didn't see on the graphics, you did not see any kind of UART. There's no chip here which directly drives a serial port. The serial port is one I/O register on the CPU, which means it is bit banked. This thing, therefore, the firmware, gets the CPU to measuring the 1 bits, if I remember correctly, in the letter B to determine how long a 1 bit takes or 0 bit takes. Let's see. B is odd. The lowest bit is 1. It's hex 4-1 or hex 6-1. So you can actually tell from the length of the start bit the bit rate that you are running at. If you hit something else, then you get the terminal noise that we just saw. Fair enough. All commands are uppercase. Get used to it. It does not do upper to lower. And if we look at the words, this would be it. If we want to have memory references, let's do a hex and do the words again, which gives us an idea where they're really located in a way that you can understand that. All the firmware words start at address 1002, that's hex. That's your second block of 4K in memory. The way this works is that when a NOVIX wakes up, when the CPU wakes up, it starts to execute code at address 4K. So the way this works so that you can add words is that at startup, the firmware copies itself to memory. The way that works is that courtesy of our little friend, this gate array over here, if you read at startup, the read commands go against the firmware, against the EEPROMs, or in this case, the EEPROMs. The write commands go against, they go against RAM. Once that's done, 1 bit gets flipped and the EEPROMs disappear from view. They've done their job. They booted the board. The board is now available, and since we are reading and writing against RAM, we can add words. This is CM Forth, unchanged, unmessed with, still the same as it came from the factory. So if you wanted to make anything persistent, you would have to burn new ones, because this board does not have any burn capability on board. If you have the source code for the for this particular version of Forth, you could recompile it and burn a new chip. Chips plural. You would have to burn new firmware into new EEPROMs or EEPROMs, switch the ones on the board, and you're good. No, that's not good. Because despite these sockets being machined, the life expectancy chip in, chip out, chip in, chip out is finite. These boards are irreplaceable. We shall not do this. If I had a newer board, and many of them, and many CPUs, I might feel tempted, but not like this. Anyway, so how do we get code into this thing? Well, This is CM4. It has an idea, or it has a concept of serial disk access. The way this works, and yes, I'm really sorry, what I'm now going to show you is going to be C code, because that right there works pretty much on any Linux box that you can lay your hands on, and I'm a great fan of making things work without loading endless tool chains. This is pretty much a very simple terminal program. Takes stuff from serial, throws it on your screen. Takes stuff from screen and throws it on your serial. And if we take a look, wait, this is a BSD box, so my PS options are a little bit different. There is a D term running against my second serial port. The first serial port is the one with the power switch on it. So we are talking on our second serial port. We are using this terminal program. What this thing does is it gets data from serial, throws it on the terminal, takes data from the terminal, throws it on serial, and we are good. Does this courtesy of a select statement. Every OS since we got sockets, so early 90s, has that. This is easily portable. So the only thing that you have to do is you have to bake into your terminal program support for the serial disk protocol. This protocol is simple, like the board is simple. It's a simple protocol. What it does is when the board wants to load or to store a block, that's the only thing it does. It loads and stores blocks. Forth blocks are 1 kilobyte in length. So the board will ask you to send or to save a 1 kilobyte block. We have some empty blocks laying around right here. Okay, this block loads other blocks, which are probably also empty. Then no carriage returns in there, so it's really just 1024 bytes of text, and they get interpreted by the board after loading. The way this works is the board sends a 0, or in some documentation it says a 3, so non-printable ASCII. And the code implements a finite state machine. If we go from idle and we catch a 0, we have a prefix. We are talking about a prefix. 0 or 3 do not show up in normal text I/O. If we have a prefix, the next byte is the block number that we want. We hold on to that and state we have the more significant byte of the block number that we want. Fair warning, this does debugging and it's chatty. If we have the MSB, the next byte coming out is my lower part, the lower 8-bit of the block number. Yeah. If the block number as a whole has its highest bit set, this is a write operation. Otherwise, it's a read operation. The block number is always the remaining 15 bits. If it's a read, I then load a block into memory if it exists. I open the file, read the file, and send the file as one big chunk into the serial port. If I could send that, this is cool. Otherwise, if it's a write operation, I catch the next 24 bytes that come out of the board and I write them to disk. Fair warning, there is no flow control. If we take a look at our connector, we have 3 wires coming out of that. There is no flow control, none. Control S and Control Q, X on, X off, are not supported. There is really no flow control. So if you rig your own with this protocol, make sure that your host, which is driving all this stuff, is snappy. This particular host is an old FreeBSD, is an old Dell GX1 that was state-of-the-art end of the 90s, probably has a 700 megahertz Pentium CPU clocked at 400 or 700 megahertz Pentium single core. Yeah, period. That's it. It will be able to do 9.6, probably also 19.2, but this is an older CPU on an older OS. So 115 kilobit might be pushing it a little bit way too far. So let's not do that. This is conservatively clocked at 9.6. Good. So what else is there? Oh, yeah. Editing capabilities in Forth may be a little bit, well, limited. And while nowadays everybody speaks Xterm or Linux, or if push comes to shove, VT220 or ANSI, back in the day, you had a boatload of different terminals and therefore different support codes. So loading the equivalent of termcap into a Forth board is prohibitively expensive, and we shall not do that. It's up to the host to accommodate the single board CPU and not the single board CPU and firmware support terminal databases. This is not how this works. Therefore, I've taken the liberty of adding another file format, this which ends in Forth, and this is a regular text file. We can load this into a regular text editor, whatever floats your boat. The only things that you have to watch out for, please not more than 16 lines. And the lines not so long that it's more than 1K. What this does is this terminal program reads each line and up to the carriage return and expands it to 64 bits and bytes and shoves that into the serial port, which means you can edit this with a text editor, as long as you keep in mind that you please do not get the lines too long, takes this stuff, shoves it into the board, and we are good. Let's demonstrate that. We are still alive. We do a 36 load, uppercase, uppercase, uppercase load. We do a 36 load. This now tells you what was happening. In main, it saw an escape, or it saw an 03, so hex 03. Changed, that triggers the finite state machine, says we are in state 1. Next byte comes in, we change to state 2, we have a block number of 0. We have a, did I do a hex on this thing? Yes, I did a hex. That was dumb. Let's try this again. Let's run this in decimal, uppercase, please. So, decimal, please. We do a 36 load. This looks better. This looks better. At the top here, we see that we switch into state 2. The higher bit of the block number is 0. It's a read operation. I then do, I hold on to the upper 8 bits of the block number, go to the next state. The block number is 36. So he's starting to send block 36. If we look at the file system, no, yes, there is no 36 BLK file. So he then goes to 36.forth, sends you what he's seeing, shows you what he's going to sends this line by line, expanded, so that we don't violate block format. Remember, we are running with default firmware. This is done sending block 36, took no time at all. It's to be expected, 9.6 kilobit back-to-back, shouldn't take much time. And comes back with, okay, so the read operation is no longer pending. We are good. We do a words, and lo and behold, this just scrolled out. Okay, fine. Let's get out of full screen mode, enlarge it so that we can get a scroll bar, and step back up. And here are my, somewhere there are my new words here. I wish this wouldn't be so jumpy. So, yeah, there they are. We go up just a little bit, line by line by line by line. And here are the words that we saw in this Forth file. They have been compiled into the lower 4K of memory where compilation starts, where compiled code gets deposited from the get-go. These bits of code, especially this memset, they originate from the attempt to load and store blocks properly, so that you can make sure that loading and saving of blocks targets the correct area in memory. There are 2 buffers, and memset are used that to overwrite these buffers with more or less, no, not random, with their own addresses to see that the subsequent load command checked something. Apart from that, this is very much a standard CM4. The only word that seems to be added after the fact is this test NOVIX EB1. Yeah, and of course, that's German. Well, good. Yeah, the board is hooked up and running. There is a simulator for the CPU, runs on Linux, which will be presented at a later point in time once it's not so awfully rough around the edges. Are there any questions?
I have a remark. I am distressed that practical programs such as the terminal emulator has to be written in C++. I think I could do it in CI4, but not in G4.
Correct. The reason why I picked that, remember, I said at the beginning, I like my stuff, I like my code to have as few dependencies as possible. The idea is because if I want to support this, and I bet there will be questions later in life, if I want to support this on as many hardware platforms as possible, having the environment coded in C, there's not even C++, the CPP is a misnomer that, well, we'll explain that when it will become obvious when we get to the simulator, because this is where this was taken from. If I want to support this on a number of platforms, Raspberry Pis, PCs running any BSD or Linux, or lo and behold, a Spark server. Yes, this will run on a Spark, on a Spark Sun or Oracle, Sun Spark. If I want to support this on a bunch of systems, then I do not want to have to walk through installations from source code of various Forth compilers to then figure out why that particular Forth version cannot talk to a serial port. If it's tricky enough to get Forth on arbitrary hardware talking to arbitrary software. I want questions, why is this terminal program not working? And for that, I shoot for the most common denominator. I found out about Forth on ESP eventually, to also find out that that particular ESP didn't have enough I/O to support all the parallel programming that I needed to write the EEPROM burner. I learned a lot about parallel I/O and SPI programming on these CPUs, but again, loading Forth and then deal with the I/O complications would have taken too much time, and it already cost me a year to get that working. So in this case, sorry about this, but I want to work with the board, not with the infrastructure of the board. Okay. I'm curious enough that I like my stuff. I want to get there, to play there. I want the way there to be as fast as possible. And since this runs everywhere, this was my poison of choice.
Can I ask the question? Does it run on the Windows?
What? This terminal program? I don't know. I don't know, because I have pretty much given up on Windows as a coding system.
Yeah, okay.
So you might get lucky with WSL, Windows Windows Subsystem for Linux, or maybe Cygwin.
Okay, but I think that with i4 running on ARM Linux 32 and 64 bits, i68 Linux 32 and 64 bits, and Windows 32 and 64 bits, you have a good chance to make a portable Windows, a portable terminal emulator that runs on a quite decent amount of systems.
True, but this is no longer my goal. Windows 10 is going to be my last Windows version, because I've had it. I've seen 11, and I'm not going to go there. My future is Linux, and honest to God, I no longer care about Windows. Windows has become a terminal, a way to get to systems where I do real stuff that earns me money,
Yeah,
stuff that entertains me.
I totally agree. I totally agree, but to accommodate my customers, I implement CI Forth for the modern systems, and in effect, the most I heard something speaking. What is that?
So
Okay.
here's the thing. Here's the thing. It depends on your requirements. You have Windows customers. I don't. I have a requirement that I want to talk to this board, and maybe others that do the same protocol. That's my requirements. I don't hook up this thing directly to a Windows PC. I hook this up to a Pi or BSD box, anything that I can easily get a serial interface on, and that runs Linux. It depends on your requirements. It would be great if you could take that source code and make it run on Windows. Be my guest. I can put this out there. Have at it. Wear yourself out. That's not the problem. My problem is, or the issue here at hand is, we have our requirements that we want to get fulfilled. In my case, I've not had Windows customers in decades. None. My stuff is Linux. Is Linux, is Solaris, is BSD. That's what I work with. That's how I make my living. So
excellent.